Alright, let's go. Number 8. The zircon discrepancy. In 2019, a team of geochemists at the University of Cologne, led by Maxwell Thiemens and Peter Sprung, were not trying to change the moon's birthday. They were running routine hafnium-tungsten isotope measurements on Apollo lunar samples, old rocks pulled from museum drawers, to refine a well-established dating technique. The point of the work was calibration. A cleaner clock. Nothing more. The textbook age of the moon sits comfortably at about 4.425 billion years, formed roughly 100 million years after the birth of the solar system. That timeline is baked into every planetary formation model taught in every university on Earth. It has to sit at that late date. Or the chemistry of Earth's early mantle does not resolve. It is one of the fixed points of the story. Their measurements did not agree with the fixed point. Thiemens, Sprung, and colleagues published in July 2019 in Nature Geoscience, in a paper titled Early Moon Formation, inferred from hafnium-tungsten systematics. Their data pushed the moon's formation to at least 51 billion years ago, roughly 85 million years earlier than the standard model comfortably permits. A follow-up in 2020, led by Bidong Zhang at UCLA, using zircon crystals from Apollo 14 breccia samples, arrived at nearly the same uncomfortable answer through a completely independent method. Contamination was the first offense. Surely the samples had been touched, handled, corrupted since 1971. The isotopy ratios said no. Sample bias came next. Maybe these particular rocks were outliers pulled from an unrepresentative slice of lunar geology. Multiple independent samples produced the same shift. Then the reset hypothesis, perhaps a later melting event, scrambled the internal clock. But hafnium-tungsten systems reset only under narrow conditions. And the pattern in the data did not match a reset signature. One by one, the escape routes closed. If the moon is that old, it formed while Earth itself was still a molten sphere of iron and silicate, before Earth had finished becoming a planet. Everything you have ever been taught about the sequence of events that produced the ground under your feet is off by tens of millions of years. What else in the story of your origin have we placed in the wrong century? The dating problem is small compared to what happens when you turn the moon around. Number 7. The far side problem. In October 1959, engineers at the Soviet space program's Oki-1 Design Bureau were focused on a narrow engineering goal: keep the Luna 3 probe's photographic film camera pointed the right direction long enough to work at all. Nobody at Oki-1 was expecting a paradigm shift. They were simply trying to get the first look at the side of the moon that never faces Earth. Physics predicts symmetry. A body that formed as a single molten sphere, cooled uniformly, and was bombarded by the same random flux of impactors on all sides should end up looking roughly the same on every hemisphere. The near side and far side of the moon should be near identical faces of the same rock. There is no obvious reason for them to diverge. They are not even close. The near side of the moon is roughly 31.2% covered by dark volcanic plains called Maria. The far side is 1%. A 2014 paper in the Astrophysical Journal Letters by Arpita Roy, Jason Wright, and Stein Sigerson at Penn State proposed that heat radiating from a still hot early Earth kept the moon's near side crust thinner and more prone to volcanism. Their model requires the moon to have formed roughly 10 times closer to Earth than it sits today, and to have been tidally locked from the beginning. Random impact statistics were the first line of defense. Perhaps the far side just got unlucky with the wrong kind of impactors. Simulations put the odds of that outcome at effectively 0. Tidal locking asymmetry was next. Could the near side, always facing Earth, pull molten rock preferentially toward one hemisphere through Earth's gravity? The math did not close cleanly. A second moon collision hypothesis, proposed by Eric Asfog and Martin Jutzi in Nature in 2011, argued that a smaller companion moon collided with the moon's far side at low velocity and pancaked itself onto the crust, thickening it. Elegant, but the isotope data has not confirmed that a second body ever existed. The moon has two faces because of something that happened in its first 100 million years. Every night you look up at exactly one of them. You have never once in your entire life seen the other with your own eyes. What made the hemisphere you cannot see so different from the one you can? From a hemisphere we cannot see to a substance that should not be there at all. Number 6. The impossible ice. In the summer of 2009, mission scientists at NASA's Ames Research Center were finalizing the trajectory for L-CROSS, the Lunar Crater Observation and Sensing Satellite. Their objective was blunt. They were going to crash a spent Centaur rocket upper stage into the floor of a permanently shadowed crater named Cabeus near the lunar South Pole, and analyze whatever cloud of debris flew up. They expected dust. They were hoping at most for a trace signal. The moon has essentially no atmosphere. In sunlit regions, daytime surface temperatures climb above 120 C. Any exposed water ice should have sublimated into vacuum over billions of years. Every model of lunar surface chemistry going back to the Apollo era treated the moon as fundamentally dry, a bone-dry rock in a hostile vacuum. That was the default assumption for 4 decades. The debris cloud lit up with water. The L-CROSS impact on 9 October 2009 kicked up a plume containing an estimated 155 kilograms of water within the observed ejecta. Anthony Colapreti at NASA Ames published the confirming result in Science in October 2010. India's Chandrayaan-1 mission, using its Moon Mineralogy Mapper instrument built by NASA's Jet Propulsion Laboratory, had already detected water signatures across broad polar regions the year before, reported by Carl Peters of Brown University in Science in September 2009. Instrument error was raised immediately, perhaps a spectral misidentification of hydroxyl. 2 independent missions, using different instruments and different techniques, confirmed the signal. Recent cometary delivery was proposed, young ice from chance collisions. Isotope ratios in some samples pointed instead to ancient hydrogen, not fresh. Solar wind implantation was suggested, protons from the sun combining with lunar oxygen. That mechanism could produce hydroxyl, but not the volumes actually measured. Each proposal explained a fraction. None explained all of it. There is water on the moon. Not much and not easily reached, but there. The nearest world to your own has been quietly holding on to a substance you were told did not exist there, possibly for 4 billion years. Possibly since before life on Earth learned to divide. How long has it been waiting there, and who put it there? Water on the moon is a surprise. The way the moon shakes is stranger. Number 5. The 10-minute tremor. Between 1969 and 1972, Apollo astronauts on missions 12, 14, 15, and 16 unpacked seismometers from their lunar landers and set them down on the surface. The engineering job was simple. Deploy a working instrument. Get home. The seismometers kept transmitting until NASA officially shut them off in 1977. And by then they had recorded something no one had planned for and no one had predicted. On Earth, most earthquakes end within a minute or two. Rock is wet, faulted, and full of pore fluid, so seismic waves lose energy quickly as they travel outward. Damping is normal. Vibrations fade. That is how a geologically active, hydrated planet behaves under seismic stress. It is the baseline expectation for any rocky world. Moonquakes ring like a struck bell. The Apollo passive seismic experiment recorded more than 12,500 lunar seismic events between 1969 and 1977. Deep moonquakes, originating between 700 and 12,100 kilometers below the surface, were shown by Yoshio Nakamura at the University of Texas Institute for Geophysics. In a series of papers published through the 1980s and refined in a Journal of Geophysical Research paper in 2005, to be triggered by tidal stress from Earth's gravity on a monthly cycle. Some individual events shook for more than 10 minutes. A few shook for close to an hour. Instrument artifact was the first thought. A seismometer stuck in mechanical resonance. Multiple stations recorded the same events simultaneously, which killed that idea. Meteorite impacts were considered, external hammering rather than internal quakes. Impact events explain a subset of the recorded signals, not the deep tidal ones. Volcanic activity was floated briefly, but the moon has been geologically quiet for at least 1 billion years. The current best explanation is that the moon's interior is extraordinarily dry, extraordinarily unweathered, and so seismic waves propagate with almost none of the damping Earth's crust provides. That answer describes the effect. It does not fully explain the mechanism. Every time you have ever looked up and seen the moon overhead, some part of it, hundreds of kilometers beneath the surface, was probably shaking. It has been shaking since before your species existed. It is shaking now. What is inside the moon that keeps ringing for an hour every time Earth pulls on it? The ringing raises a deeper question about what the moon is actually made of. Number 4. The missing core. In 2011, a team led by Renee Weber at NASA's Marshall Space Flight Center was not launching a new mission. They were re-examining data, the same Apollo seismic records that had been sitting in NASA archives for nearly 4 decades. They applied modern array processing techniques borrowed from terrestrial seismology to signals no one had been able to fully parse in the 1970s. Old data. New tools. Quiet work. Earth's iron-nickel core makes up roughly 55% of the planet's radius. A body formed in the standard giant impact scenario, where a Mars-sized object called Theia struck early Earth and threw off the debris that became the Moon, should retain a core roughly proportional to a differentiated rocky world of its size. Estimates varied across the pre-2011 literature, but every model expected a core on the order of 1/3 to 1/2 the Moon's radius. The core they resolved was tiny. Weber and colleagues published in Science in January 2011 a reanalysis showing the Moon has a solid inner core with a radius of about 240 kilometers and a fluid outer core reaching to roughly 330 kilometers. Total core radius, around 20% of the Moon's radius of 1,737 kilometers. For comparison, the same figure for Earth is more than 50%. The Moon is structurally wrong for its size. A late-stage core loss was proposed, perhaps a subsequent impact stripped iron away. No corresponding basin large enough to have caused that impact has ever been mapped. An incomplete differentiation was suggested. Maybe the Moon simply never sorted its iron efficiently into a core. But surface iron abundance is too low for undifferentiated iron to be hiding in the crust. The Theia composition variant was floated. Maybe Theia was iron poor to begin with. That solves the core problem and immediately creates a bigger one. It becomes harder to explain why Theia's isotopic fingerprint vanished so cleanly from the record. The Moon does not have the interior it should have. The body that stabilizes Earth's axial tilt, sets the tides that shaped every coastline you have ever walked, is built wrong on the inside. What kept the Moon from forming a proper core? Or what took it away? A body built wrong on the inside is now, quietly, leaving. Number 3. The receding companion. On 21 July 1969, before he climbed back into the lunar module, Buzz Aldrin unfolded a small suitcase-sized panel of corner cube reflectors and set it down on the surface at Tranquility Base. It was engineering hardware for a specific scientific question: how far away, exactly, is the Moon at any given instant? Apollo 14 and Apollo 15 added more reflectors. 2 Soviet Lunokhod rovers deployed additional ones on the far western Maria. In a stable 2-body system with no external influences, the Moon should hold a roughly constant orbit around Earth for billions of years. Small perturbations from the Sun, Jupiter, and Venus exist, but the orbit should not steadily unwind. It should not be measurably running away from Earth. Certainly not at a rate detectable by the tools of a single human generation. It is running away, and we can watch it. Laser ranging experiments carried out by observatories including Apache Point Observatory in New Mexico and the Grasse Station in France have measured the Earth-Moon distance to within a few millimeters for over 5 decades. James Williams and Dale Boggs at NASA's Jet Propulsion Laboratory reported in the journal Celestial Mechanics and Dynamical Astronomy in 2016 that the Moon recedes from Earth at 3.8 centimeters per year, a value stable to remarkable precision across every measurement window. The recession itself is not the mystery. Tidal friction on Earth transfers angular momentum outward to the Moon, and the physical mechanism is well understood. The mystery is what happens when you run the tape backwards. Extrapolating the current rate linearly places the moon inside Earth's Roche limit only about 1.5 billion years ago, far later than the moon's known age of over 4.4 billion years. Something changed in the deep past. Continental configurations, changes in ocean depth, altered tidal resonance in Precambrian seas have all been proposed. No single model reproduces the full history cleanly. The moon was closer once. Days on Earth were shorter. Tides on the coasts of a young planet were mountains high. Something you cannot see keeps pushing it away from you at the speed a fingernail grows. Where was the moon, really, when the first cell on Earth learned to divide? The moon is leaving. The moon may also never have belonged. Number 2. The isotopic identity crisis. Through the 1970s and 1980s, geochemists at institutions including the University of Chicago and the Max Planck Institute in Mainz set themselves a task that sounded unglamorous. They wanted to measure oxygen isotope ratios in every kind of rock they could get their hands on, meteorites, Earth samples, and lunar samples returned by Apollo. Isotope ratios are effectively planetary fingerprints. Different bodies in the solar system form with different ratios, and once measured accurately, those ratios do not lie. The giant impact model, developed in the 1970s and 1980s by William Hartman, Donald Davis, Alastair Cameron, and William Ward, predicts that most of the moon's mass came from Theia, the hypothesized Mars-sized impactor. Since Theia formed somewhere else in the early solar system, its isotopic fingerprint should differ measurably from Earth's. Simulations put the moon at roughly 70 to 90% Theia material. That is not a small fraction. It should be visible. The moon's isotopes match Earth's almost exactly. Uwe Wiechert at the Open University reported in Science in October 2001 that the oxygen isotope difference between Earth and Moon samples was smaller than 0.005 per mil, statistically indistinguishable. Junjun Zhang and colleagues at the University of Chicago extended this in Nature Geoscience in 2012 to titanium-50 isotopes, with the same result. Later work covering tungsten, chromium, silicon, and even iron isotopes has repeatedly confirmed the identity. Every fingerprint keeps saying Earth. A slow, thorough post-impact mixing of Earth's mantle with the debris disk was proposed, enough turbulent stirring to homogenize both bodies. The mixing timescales required are longer than the disk itself is thought to have survived. A high angular momentum impact variant was proposed by Matija Ook and Sarah Stewart in Science in 2012, spinning early Earth so fast that a smaller impactor could contribute far less material. It works, but demands a very specific pre-impact Earth spin rate. Others have argued Theia happened to form in the same orbital neighborhood and shared Earth's composition by coincidence. A statistical unlikelihood that is difficult to test. The best theory for how the moon exists requires the moon to be mostly something else. The moon insists it is mostly Earth. One of those claims is wrong, and the wrong one is fundamental to the story of your planet. If the moon is not made of Theia, what is it made of? And what was Theia? If the moon has an identity problem, the sky itself has a coincidence problem. Number 1. The eclipse coincidence. The measurement that anchors this entry was not made by a modern lab. It was made repeatedly, imperfectly, by astronomers going back to Hipparchus in the 2nd century BC, refined by Aryabhata in India in the 5th century, sharpened by Tycho Brahe in the 16th century, and finally locked down to millimeter precision by lunar laser ranging in the 20th. Every generation kept asking the same disarmingly simple question. How big does the moon look from the surface of Earth? The angular size of an object in the sky is set by its physical diameter divided by its distance from the observer. There is no known physical principle in celestial mechanics that requires two independent bodies, the sun and the moon, to end up with a ratio of diameters that almost exactly cancels their ratio of distances. It should be a coincidence, if it happens at all. It should not be the rule. It happens, and it happens now, in your lifetime. The Sun has a diameter of about 1,392,000 kilometers and sits at an average distance of 149,600,000 kilometers from Earth. The Moon has a diameter of 3,474 kilometers and sits at an average distance of 384,400 kilometers. The two angular sizes agree to within roughly 2%. That agreement is why total solar eclipses reveal the Sun's outer corona so cleanly, a phenomenon documented in detail by Sir Norman Lockyer, who used solar eclipse observations to identify helium in the solar spectrum in 1868 before the element had ever been detected on Earth. Anthropic selection was proposed. Observers arise on worlds where interesting eclipses happen to be visible. But of every planet-moon system in the solar system, none produces total eclipses this cleanly. Jupiter's moons are too big for their distances. Mars's moons are too small. Tidal evolution was proposed as a temporal coincidence, the moon used to look larger in the sky, and in a few 100 million years it will look too small to fully cover the Sun. True, but it does not explain why the match is nearly exact right now, in the narrow epoch during which humans developed the ability to notice it. Divine design, common in older literature, is unfalsifiable and has no place in the analysis. No secular mechanism has ever been offered that promotes the ratio to a physical law. You were born inside a window of roughly a few 100 million years, during which a rocky planet's only large moon lines up with its star with almost surgical precision. Before this window, the moon was too big to reveal the corona. After it, too small to cover the disk. Right now, you can see the Sun's corona with your own eyes. If you stand in the right place at the right minute of the right decade. Why does the sky above your species look, at this particular epoch, exactly like this? The moon is not a mystery because it is far away. It is a mystery because it is close, familiar, and refuses to fit the theory that says it should be there. Every anomaly on this list, the isotopes, the core, the shaking, the ice, the size in the sky, sits inside the best-tested corner of planetary science. The universe is not confused about the moon. We are. If you want to see more videos like this, click the video on screen now.